Hello everyone, welcome back. A quick recap of what we've done in the last couple of lectures. So we've talked about sequences and then series, and then we talked about five convergence tests for series, three of which apply to uh, all series, and the rest two are specific to geometric series and P series. And the three general convergence tests are the ratio test, the comparison test, and the limit test. So that's what we've done in the last two lectures. And all the series we've encountered so far are summations of numbers. So it's a sum of A1, A2, A3, A4, A5, and A1, A2, A3, A4, A5, they are all just numbers. Today we're going to start with power series. Power series is a series, but different from the series we've seen so far. It's actually a summation of functions, as you will see. The definition of power series is given as follows. If x is a variable, then an infinite series of the form this, and from 0 to infinity, an x to the n. If you were to expand this sigma notation, you get a0 plus a1x plus a2 x squared plus a3 x cubed plus dot dot dot. An infinite series of this form is called a power series. So notice that each term is a function of the variable x. We can even generalize this definition and define something similar but a little bit more general. So an infinite series of the form an times x minus c to the n, where c is some fixed constant. This equals a0 plus a1 times x minus c plus a2 x minus c squared, so on and so forth. This is a power series centered at C. So we can extend this standard definition to include an arbitrary constant C, and get this and use this definition as a power series centered at C. Okay. All right. Let me give you a quick example. For example, the sum and from 0 to infinity, xn divided by n squared is a power series with an equals 1 over n factorial, right? Because an is the coefficient in front of x to the nth power, and in this case, it's just 1 over n factorial. And this, and from 0 to infinity, x plus 1 to the n is a power series centered at -1 with an equals just 1. Okay, so 2 examples of power series. Now, of course, just like any other series, when we talk about series, what we care most, of course, is the convergence theorems. So when does a power series converge? Now, here is a very elegant theorem that tells you convergence of a power series. So here's a theorem that tells you what the domain of convergence can look like. First of all, if we go back to the definition of the power series, we notice that it is actually a function that depends on x. So what do we mean when we talk about convergence? We mean does the power series converge for some values of x? And for those values of x where the power series converge, then we call that the radius of then we call that it's in the range of convergence. Let me write all of this down before we introduce the convergence theorem. Okay. For a power series, centered at C, if, say, alpha is in the domain of the variable x, and the series, the sum, n from 0 to infinity, an of a minus c to the n converges, we say the power series infinity an x to minus c to the n, this power series converges at x equals alpha. So essentially, we're just saying that if some alpha is in the domain, then we replace the x with alpha, and if that series that series will then be a summation of some numbers, and we can determine if that series converges or not. And if it converges, then we say the power series converges at x equals alpha. Okay, and also the range of convergence will just be all the points where where the power series converges. So the range So let me say this, the range of convergence is all the points f in the domain of so maybe I should f alpha in domain and n alpha minus c to the n converges. All of this just says that the range of convergence is all the points in the domain where the power series converges. Okay, and then we can talk about the convergence theorem. As it turns out, for a power series, you can only get three types of range of convergence. You can't just get arbitrary points where the power series converges. It either converges only at the center, x equals c, or it converges on some interval around c, or it converges on the entire real line. So that's the theorem for the convergence of power series. It says for a power series centered at C, precisely one of the following is true. The first one is the series converges only at C. So the power series converges at only one point and diverges everywhere else. Or the series, let me just phrase it the same way the book does. There exists positive real number exists R that's positive, and maybe should exists R as a real number such that R is positive, and the series, I'm sorry, the phrasing is weird. Exists R that's a real number and a positive such that the series converges for all the points that is within distance R of the point C, and diverges for points that are more than distance R away from the C. So if you look at the real line and say this is the point C, then your range of convergence in this case will be an interval around the point C with R as the radius of this interval. Okay, and in the first case, your range of convergence would just be this single point C. And the last scenario is that the series converges for all x in R, for all real number. So that tells you that the entire real line is the range of convergence. If we use shaded area to represent the range of convergence, then this will be the part that's inside the interval. Note that we claim nothing about the endpoints of the interval. This is a strict inequality. Okay, we claim nothing about the convergence at the endpoints. That's actually a difficult problem for some power series. For some power series, I mean, you just have to determine the convergence at the endpoints manually. So for some power series, they're easy. to be determined, but for some power series, it's actually quite complicated. All right, so we have these three cases. So it's either converges at only one point, or some interval, or the entire real line. Note that um, note that the first case has the smallest range of convergence. So no matter which scenario the power series belongs to, it always converges at the center C. The reason is very obvious, because if you look at the definition, you get right here. If you look at the definition, it's a sum of an times x minus c to the n. Now, if you plug in x equals c, you get the sum of zeros, which is zero. So it just means any power series will converge at the center. There doesn't exist a power series where that doesn't converge anywhere. So it has to converge at the center at least. Okay. Next, let's find the radius of convergence. The first problem is find the, oh, maybe I should write this. And in this case, R is called the radius of convergence. Let's find the radius of convergence of the power series sum n from 0 to infinity minus 1 n x plus 1 and 2 to the n. Okay. So in this case, the coefficient, in this case, this is a power series centered at -1, because it's x plus 1 in the parentheses, and the coefficient in front is -1 to the n divided by 2 to the n. Now we have this is, we can write this as an times x plus 1 to the n, where an equals -1 to the n divided by 2 to the n. This is just so that we can we can write this out more succinctly, I guess, because you don't want to repetitively write this fraction every step of the way. Next, we apply the ratio test. The series, so by ratio test, the series converges when the limit of n go to infinity of an plus 1 times x plus 1 to n plus 1th power divided by an times x plus 1 to the nth power is smaller than 1 and diverges when the limit is larger than 1. That's what ratio test tells us. So we can use this to obtain the radius of convergence. Now we just have to look at what this limit really is. Limit of n go to infinity of absolute value of a n plus 1, x plus 1 to the n plus 1 divided by a n times x plus 1 to the n. Now this is the limit absolute value of minus 1 to the n plus 1 divided by 2 n plus 1 times x plus 1 to the n plus 1. And then it's a fairly large fraction, but the arithmetics is pretty straightforward. And then we have minus 1 to the nth divided by 2 to the nth, and then x plus 1 to the nth. Okay, so after canceling out certain terms, we get this equals the absolute value of minus 1 to the n divided by 2 times x plus 1. Because x plus 1 to the n plus 1 divided by x plus 1 to the nth, you're left with x plus 1. And then you have 2n divided by 2n plus 1, 2 to the n plus 1, you get 1 over 2. And then, oh, sorry, so this is, my bad, this is not minus 1 to the n, this is just minus 1. So we get minus 1/2 times x plus 1. Alright, since we're in the absolute value, the minus sign doesn't really matter, so we have the limit of n go to infinity of 1/2 x plus 1. Now, from this, we get the limit of an plus 1, x plus 1 to the n plus 1 divided by an x plus 1 to the n is smaller than 1 if and only if I forgot to write this. Since notice that the stuff in the absolute value doesn't depend on n at all, so we can get rid of the limit because we've canceled out everything that depends on n, and the things that follows the limits that follows the limit sign doesn't depend on n at all. So we have this equals just x plus 1 over 2, the absolute value of x plus 1 over 2. So the limit is smaller than 1 if and only if x plus 1 is smaller, divided by 2 is smaller than 1, and of course we get x plus 1 divided by 2 is smaller than 1. Tells us is equivalent to writing I suppose it's equivalent to writing minus 1/2, sorry. Is equivalent to writing minus 3 is smaller than x smaller than 1. Because you multiply both sides by 2, you get x plus 1 is smaller, absolute value of x plus 1 is smaller than 2. And then you get, right, so you get minus 2 minus 1 to 2 minus 1. So you have x is between minus 3 and 1. Maybe I should write out the calculation here. X plus 1 over 2 smaller than 1 is the same as x plus 1 is absolute value of x plus 1 smaller than 2, which is the same as minus 2 smaller than x plus 1 smaller than positive 2, and subtract 1 on every one of these, you get minus 3 smaller than x smaller than 1. Therefore, the power series converges on this interval -3 to 1 and diverges outside this interval, and then the radius of convergence is equals 2. Okay, the radius convergence is just 1/2 of the length of this interval. So you get 4 divided by 2, which is 2. All right, that's the first problem. All right, similarly, let's look at the radius of convergence of another power series. Find the radius of convergence of the power series going from 0 to infinity x to the n divided by n factorial. All right, so first, let me rewrite this in terms of an, just because that will make the notation look a little simpler. An times x to the n, where an equals 1 over n factorial. And once again, using the ratio test, by ratio test, the series an times x to the n converges when the limit of n go to infinity of an plus 1 x to the n plus, I should write a fraction, an plus 1 x to the n plus 1 divided by an times x to the n is smaller than 1 and diverges So it's the same argument. We just use the ratio test and see when the limit is larger than 0 and when the limit is smaller than 0. All right, then the limit, plugging in the an plus 1 and an, we get that the limit of this is actually the limit of 1 over n plus 1 factorial times x to the n plus 1 divided by 1 over n factorial times x to the n. Now that's just n factorial divided by n plus 1 factorial times x. And that is the limit of n go to infinity of x over n plus 1. Now, the limit of this is 0 for all x in R, for all real number x. The reason is, pick any x, fix x. Then if x is fixed, if x is fixed and n is an increasing number, then x is bound to exceed n is bound to exceed x at some point. Since n is getting larger and larger and larger, while x is a fixed number, and you're dividing a fixed number by a super large and growing number, you get limit 0. Okay, this is just a simple application. This is just a simple calculation of the limit, because in this case, x is a fixed number. So you treat it as a constant because we're taking the limit of n go to infinity, and x is treated as a constant here. And the limit of 1 over n plus 1 is obviously 0, then the entire limit is 0. So what does it tell us? It tells us that by the ratio test, the series converges for all x. For all real number x. And so that's actually the third case in the convergence theorem. And it's equivalent to say that the radius of convergence is r equals infinity. Right? Because it's a real line, you can consider the real line as an interval with radius infinity. Now, the reason we study power series is that it is in the form of a polynomial. So if you look at the term, each term is a coefficient times x to the nth power. This is like an infinite polynomial, and polynomials have very nice properties. So the question then becomes this: suppose we have some function f of x. Can we represent the function as a power series? That's what Taylor and Maclaurin series, Taylor series and the Maclaurin series are about. So let me write that here. Goal: given, yeah, let me change the font. Okay, goal. Given a function f of x, can we represent f of x as a power series? Okay, as I said, power series have very nice properties. It's easier to study. Suppose you have some super complicated function f, like it takes 2 lines to write out the function explicitly. There's just no way, it's very complicated to study it's very difficult to study these functions, because when you look at the derivatives, I mean, you want to differentiate this and you have to differentiate that super long function. It's just not practical. So, but if we can represent it as a power series, then polynomials are very easy to differentiate, integrate, we can do all sorts of operations on it. So, Taylor series and Maclaurin series are sort of an answer to this question. Let's first write out Taylor series, or actually Taylor's theorem. If f is represented by a power series centered at C, then the power series has the form f of x equals the sum, and from 0 to infinity, of n of c times x minus c to the n divided by n factorial. And this notation with n in the subscript is this is the nth order derivative. Of course, when you put c inside parentheses, you're just evaluating the derivative at x equals c. So it tells us that if we know that f can be represented by a power series, then the power series has to be this one. The proof is actually very simple. So we go about it this way. If f can be represented as a power series centered at c, then we're saying this, right? So f equals some power series centered at c with unknown coefficients an. Now we just look at the derivatives. We first look at a zeroth order derivative. Now the zeroth order derivative is just f itself. So f of c equals the sum n from 0 to infinity an times 0 to the n. Now 0 to the nth is 0 if and only if n is not 0. When n is 0, 0 to the 0th power is actually 1. So we have, this is just a0. We've proved that a0 equals f1, and then the first order derivative Now, to make the process a little easier, let me write out the expansion of this summation. We have a0, a1 times x plus a2 times x squared plus, x minus c instead of x here. a1, x minus c plus a2, x minus c to the squared plus dot dot dot. Okay, if you look at the first order derivative, you get f prime of c. Well, this equals the derivative with respect to x of this entire thing. Well, yeah. So just the derivative of this thing evaluated at x equals c. Yeah, let me just write this. So this notation means taking the derivative with respect to x, and of a0 plus a1 x minus c plus a2 x minus c squared plus dot dot dot. And this means evaluate this at x equals c. Okay, this notation just means take the derivative and then evaluate that at x equals c. Now, the zeroth order term is a constant. If you take a derivative with, if you take the derivative of a constant, you get 0. And the derivative of the second term, this term, first order term, is just a1 because it's a1x. The derivative of a1x is a1. And the derivative of a2 x minus c, you get 2 times a2x. So you get stuff like this. A1 plus 2 times a2x. I mean, if you go on, eventually you'll realize you get like 3 times a3x squared plus 4 times a4x cubed, so on and so forth. And all of that evaluated at x equals c. Or what have I done? Sorry. Why do I keep forgetting the x minus c part? It's 2 times a1 times x minus c plus 3 times, right, it's 3 times a3 squared times x minus, x minus c squared, and then plus 4 times a4 times x minus c cubed, so on and so forth. Now all of this evaluated at x equals c. Notice that since x minus c is involved in every single term starting the second one, then all of that equals 0. So we are only left with a1. So that tells us a1 has to be f prime of c. And if you just continue this process, eventually you'll realize that if you take the nth order derivative, oops, you'll find that the left-hand side is the nth order derivative of f evaluated at c. And if you take the nth order derivative of this summation, you'll find that this is actually x times n times n factorial. N factorial times a to the n. So you can visualize it like this. If you take the second order derivative, then you're taking one more order of derivative on top of this, and then the a1 disappear, right? Because if you take the derivative of a1, you get 0. And if you take a derivative of the second term, you get 2 times a2, so 2 factorial times a2. Now if you take the derivative of the third term, you'll still end up with x minus c in the result. If you evaluate that at x equals c, that term disappears. So that means if you take the second order derivative at x equals c, all you're left with is 2 times a2. And if you continue in that pattern, then the nth order derivative of this power series will be n factorial times an. So that tells you an equals the nth order derivative of c divided by n factorial. And that concludes our proof, because that is exactly this expression we have in the theorem. Okay, so this tells you that for any function to have a power series representation, it has to be given by the derivatives of that function. Now, that is the definition of Taylor series. So given a function f of x in some c in the domain of this function, the power series given by this expression, exactly what we had before, is called the Taylor series of f centered at c. And a Maclaurin series is just it's a special type of Taylor series. It's a Taylor series centered at 0. So it's just a special Taylor series with C equals 0. All right, with this definition in mind, let's look at this example. We want to find the Maclaurin series of f of x equals e to the x. Remember that Maclaurin series is Taylor series centered at 0. So plugging in the formula, we get the Maclaurin series is first of all, for the first step is to find all orders of derivatives of the series, right? Now, the 0th order derivative is e to the x, and therefore the 0th order derivative evaluated at 0 is 1. Because the Maclaurin series is Taylor series centered at 0, so we plug in 0 into x, right? Our c is 0 here. All right, so to continue, we find the first order derivative. Now why am I writing this? I mean, the first order derivative is just f prime. The derivative of e to the x is e to the x itself. So we get the first order derivative evaluated at 0 is once again 1. And then the second order derivative is, well, again, e to the x. Then f double prime of 0 is 1. Essentially, we have the nth order derivative is e to the x itself, and the nth order derivative evaluated at 0 is 1. Because the function is e to the x, no matter how many derivatives you take, you end up with the function itself. So we figured out that all the derivatives evaluated at 0 will be 1. So we just plug that into our expression here with c equals 0 and the derivatives being 1. So we get f of x, that's e to the x. Remember that the expression is this, n equals 0 to infinity times x to the n divided by n factorial. Now we've proved that the derivatives are 1s, so we get n equals 0 to infinity of x to the n divided by n factorial. Alright, so we've shown that the function e to the x has this Maclaurin series representation. And let's also find the radius of convergence for the Maclaurin series. And I should write that in the problem as well. Okay. To determine the radius of convergence, we'd use the ratio test. Take the limit of and go to infinity. I'm not going to write all of that again, but just keep in mind that the n plus 1th term is obtained by replacing n by n plus 1. So we get x to the n plus 1 divided by n plus 1 factorial divided by the nth term, which is x to the n divided by n factorial. Now this is the limit of x over n plus 1, which is 0 for all x on the real line. So it tells us that the radius convergence convergence is r equals infinity. Okay, and that tells us f of x indeed equals this. Yeah, I probably shouldn't write this. Okay, another practice problem. This time, not a Maclaurin series, but a Taylor series centered at 1. Find the Taylor series. For the function f of x equals 1 over x, centered at 1. Okay, as always, we first take the derivatives. Well, the 0th order derivative is f of x, so that equals 1 over x, and then f of 1 equals just 1, then f prime of x equals, well, this is x to the minus 1. Let me rewrite 1 over x as x to the minus 1. Then f prime is minus x to the minus 2. And f of 2, f prime of 1 is minus 1. And f double prime of x is 2 times x to the minus 3, right? Because you multiply minus 1 with minus 2, you get positive 2. And then f double prime of 1 is 2. F triple prime of x is minus 6 times x to the minus 4, and then f triple prime 1 is minus 6. Now, the pattern for this is the nth order derivative is going to be minus 1 to the nth power times n factorial times x to the minus n minus 1. So minus n parentheses plus 1. And the nth order derivative evaluated at 1 is just going to be minus 1 to the n times n factorial. The reason is this. Every time you take a derivative, you get a minus sign because the exponent is always negative. So every time you take a derivative, you get one extra minus sign. The nth order derivative is n times differentiation, so you get minus 1 to the nth power. And also, since the exponent keeps decreasing from minus 1 to minus 2 to minus 3 to minus 4, every time you get a multiplication of the new lower exponent, and that's why you get a multiplication of 1, then 2, then 3, so you get n factorial here. And then x to the minus n plus 1, because you start with the exponent minus 1, and then after each differentiation, the exponent decreases by 1. So after n differentiations, the exponent is minus 1, then minus n. So you get minus n plus 1 here. All right, then plug in x equals 1, you get this, minus 1 to the nth power times n factorial. Now the Taylor series centered and instead of writing these words, let me just write 1 over x. So f of x equals 1 over x equals 1 over x. Now this equals the sum, and from 0 to infinity, of the nth order derivative evaluated at 1 times x minus 1 to the nth power divided by n factorial. This equals the sum, write another line, this equals, and from 0 to infinity, f of n, so, plugging in the nth order derivative, that's minus 1 to the nth power, times n factorial times x minus 1 to the nth power divided by n factorial. And this equals the sum from 0 to infinity of minus 1 to the n times x minus 1 to the n. Now, if you want to expand the summation, what you will end up with is 1 minus x minus 1 plus x minus 1 squared and minus x minus 1 cubed, so on and so forth. So you get an alternating sign and an increasing exponent of x minus 1. Now, actually, although I wrote the equal sign, this is not so rigorous. This equality turns out to hold actually for only for x larger than 0. If you consider x equals 0, then it obviously the equality obviously doesn't hold, right? Because you get 1 divided by 0, which is undefined. So it turns out that this equality only holds for x larger than 0. Now you can of course determine the range of convergence for this Taylor series, but whether or not the Taylor series converges to the original function itself, that's another issue, and that's actually something that we won't cover in this in this course. But I'm just telling you that in this case, it actually converges back to the original equation for x larger than 0.
Okay, so that's all for today. Now we haven't finished chapter 10.4. I will assign the web work assignments today, but it won't be due till Wednesday next week, because we haven't finished 10.4. So at the beginning of next lecture, we will continue our discussion on power series. We will talk about power series of some basic elementary functions. One example would be the exponential, that one we did today, but also like 1 over 1 plus x, and also some common trig functions like sine and cosine. And we will go over some examples where we can use the power series of these elementary functions to get more complicated power series. And then we'll move on to 10.5, Taylor polynomials. And by the end of next week, we'll probably go over Newton's method. All right, so that's all for today. I'll see you all next Monday.